Hello, beautiful people who seem to exist within a space outside of space and time, the internet. What's Gucci? Today we'll be doing momentum and introducing you to the concept of conservation, which is a very important concept in physics and in life. But I've made this worksheet on momentum. You have the key theory you need, which I'll go through in a minute. And you have all of the questions from as far back as 2015, so 8 years of questions, all on momentum here on this worksheet, and you have all of my written answers as well here. So this is a really good resource, so make sure you download that and go through it. But let's talk about momentum. Okay, so momentum. What is momentum? Well, momentum can be defined as a mass in motion. And if you've noticed, there's a lot of mass and a lot of it is in motion, as I talked before in my previous video on kinematics. And so this is an important property of masses that are moving, and it's equal to the product of the mass and the velocity. So momentum can be defined as mass times velocity. And a very important concept here that we need to understand is that momentum, like many properties, including energy, is conserved. And that means that the momentum before an interaction or collision equals the momentum after that collision or interaction. And as momentum is defined by mass and velocity, velocity being a vector, momentum is also a vector. So this conservation is happening in both the x and y direction. So you have a momentum of a mass, and all of the momentum in its x direction initially will equal its momentum in its x direction final, like after the interaction, and same goes for the y. So its initial y and x components will equal its final y and x components. And we'll see that when we do an example. But I have a basic example here. You can see if you have two masses coming together, they collide, you have their final velocities and their initial velocities. Well, if momentum is conserved, well, the sum of their momentums, the total momentum before the interaction or collision equals the momentum after the interaction or collision. With this simple example, they're all acting in the x direction. But as we'll see in the questions that we have to deal with the y direction as well. Quick notes on relative velocity. This is actually very important. And as you go deeper into physics, relativity is really a main point of interest for physicists, because everything is actually relative. But you just have to understand that relative velocities here. So let's say you have a ball moving at 3 meters per second to the left and a ball moving at 2 meters per second to the right. Well, relative, so if you were moving with the ball, this ball moving towards that ball, well, it would look like it's moving at 5 meters per second, right? Because it's coming at you at 3 meters per second and you're moving at it at 2 meters per second. So the relative velocity of, let's say, ball A, which is moving towards you, and you're on ball B, well, it'll look like it's moving at 5 meters per second. So it's just the appearance of velocity. Then we have to understand elastic and inelastic collisions. Basically, it's just whether energy, kinetic energy, is being lost or not. Elastic just means the initial kinetic energy will equal the final kinetic energy, and inelastic is, well, kinetic energy has been lost, so the initial kinetic energy will be greater than the final kinetic energy. They won't equal each other because you've lost some energy during the interaction. And finally, I will do a complete separate video on Newton's laws of motion, but because momentum is directly related to force, as seen here, force equals the change in momentum over time. Well, Newton's laws are actually quite important, and they ask it frequently within the momentum question itself. So you can read through that. I'm not going to go through it. We'll go through it in detail later. But it's basically 3 simple laws for forces and how forces work, and they're universal. Yes, that's all the theory you need. Not too difficult, I don't think, but we'll consolidate it with questions right now. Let's do some questions. Exam questions, my favorite. Okay, so we'll be doing 2 today, and it will cover pretty much everything. And you'll see as you go through the worksheet, they're pretty similar. I'm seeing some serious similarities in this question. So state the principle of conservation of momentum. Well, this is just simply the total momentum. See how my writing is today. Is constant. It doesn't change. We can have a bunch of collisions, interactions, but the total momentum is constant in a closed system. And a closed system just simply means that there's no external forces acting on the system. Nothing's coming in from outside of the interactions that we're concerned with. Okay, a ball moves along, so it's just describing this diagram. So we have ball A and ball B. Ball A is moving towards ball B, and then they collide, and they go off like this. They have certain masses and certain speeds or velocities at the start and at the end, and they're moving off at different degrees. Remember that these, they'll be made up of x and y components because they're moving at angles. So by considering the components of the momentum at the right angles to the direction of the initial path of A, so they're talking about this direction, which is also called the y direction, calculate theta. Well, this just comes down to your understanding of conservation of momentum. So initially, if we're thinking about the y direction here, initial momentum in the y direction, py just means momentum in the y direction. Well, this is 0. There's no components here in this A and B initially, or they collide, acting in the y direction. So the initial momentum in the y direction is 0. The final momentum in the y direction, what does this equal to? Well, this is going to equal to the sum of the y components of the momentum of A and B. So for A, so this momentum vector will be made up of an x and y component, right? Here and here. So this is py. And what is py? Well, we can say that sine theta equals py over its momentum, which is going to be m, the mass of A, times the velocity of A, right? So py is just mass of A times velocity of A times sine theta, right? And that's just the momentum of A. So you could just say PA. So it'd be the mass of A times PA sine theta. But then it's also what contributes to this final momentum, the total final momentum, is also the momentum of the y direction of B. However, it's acting in the opposite direction. So it'll be minus, and here the py of B, this is just going to be doing the same thing, but it will be minus m of B, v of B, sine of 30 degrees. So minus mb, vb, sine of 30 degrees. Okay, so therefore, as momentum is conserved in both x and y directions, well, that means that 0 is going to equal to this. So therefore, we get 0 equals to, well, ma, mass of A is 4, velocity is 6, times sine theta, which we want to find, minus the mass of B is 12, and the velocity is 3.5 times sine 30 degrees. Okay, so we can take this stuff over and we'll get, well, 24 sine 4 times 6 sine theta equals 2. Where's my calculator? 12 times 3.5. So this gives us 42 sine 30 degrees. Okay, so we can divide through by 24. And then, therefore, theta will just equal to the inverse sine of this. 42 times sine 30 divided by 24. Shift sine. So just to be clear, I calculated this and I got sine theta equals to 0.875. So therefore theta will be the inverse sine. I don't give you enough room. It triggers me so much. 61 degrees. So rounded is 61 degrees. 61. Use your answer in I to show the initial speed of V. Okay, it's 12. So we want to find this. What is this? Well, because it's acting in the x direction, we can just look at the conservation of momentum now in the x direction. So we can say, you know, the initial momentum in the x direction, well, this is just mass times velocity from the mass. So this would be the mass of A times the velocity of A, or u of A, the initial velocity of A, which is just going to be 4 times V. And so final, and this, remember, this is going to be equal to the final momentum. Excuse me. And this is going to be, well, I'm going to need a little more room. Final momentum in the x direction. Well, it's the same thing that we did here, but instead of sines, it's now going to be causes, because we're looking at these components here, the x components of these A and B momentums. So it's going to be the same, doing the same thing. Would be mass of A times the velocity of A times cos of theta, which we know is 61. This first one, and if the second one, now it's going to be plus, right? Instead of minus, it's going to be plus, because they're both of the x components of these A and B momentums are acting in the same direction. Here, one was acting up and one was acting down. In this case, they're both acting to the right. So they're both positive. Plus the mass of B, velocity of B, cos of 30 degrees. All right, remember, these are just found by doing the same thing here. So in this case, it would be cos theta equals to px, so the opposite adjacent, px, px divided by the mass of A. Right, you rearrange that, you get MAVA times cos theta. Same for that as well. So therefore we get 4V equals to this. The mass of A is 4 times 6, the velocity of A, 4, 6 cos 61, plus the mass of B, 12 times 2.5, times 3.5 cos of 30 degrees. So therefore, we get 4V equals to whatever this sheet is, plus 12 times 3.5 plus 30. Okay, so it's 48. This all the stuff equals 48. Therefore, V will equal what? 12 meters per second. So the velocity initially of A is 12 meters per second. By calculations of the kinetic energy, state and explain whether the collision is elastic or inelastic. Well, if the kinetic energy before equals the kinetic energy after, well, it's elastic, and the kinetic energy before does not equal to the kinetic energy after, then it's inelastic. So we just calculate those kinetic energies. So initial EK is going to be a half times the mass of A times the velocity of A. So the mass of A times V, let's call it U of A for now, squared, plus a half times the mass of B times U of B squared. That's the total and initial kinetic energies. So it's going to be 4 times V, a half of 4 times U of A, which was this, 12 squared, plus, well, this is going to be 0, right? Because B isn't moving. So it's going to be plus 0. So just this. This equals 2. 4 times 12 squared divided by 2. It's 288 joules. 288 joules. And then the final EK going to be a half mass of A times the final velocity of A squared, plus a half mass of B times the final velocity of B squared. Well, those things are just going to be half 4 times 6 squared plus a half 12 times 3.5 squared. So 4 times 6 squared divided by 2, 72 plus 6 times squared, 145.5. Okay, 145.5 joules. So clearly there's a lot, we've lost kinetic energy here. Started with 288 and we've ended up with 145. So, you know, because the initial EK does not equal, or I guess it's greater than the final EK, collision is inelastic. Cool. We'll do one more. This will just, this one will show us a bit about forces. It's from, I think it was Newton's, yeah, it's Newton's second law. The force is related to the change, or the rate of change in momentum. So we have some block with some momentum, block X, moving towards block Y. There's no resistive forces, so it's frictionless. And we have the variation of momentum on block Y as time progresses here. They collide, and obviously block Y's momentum then increases as they're colliding. So define linear momentum, well, it's just mass times velocity. Determine the time interval over which the blocks are in contact. Well, the blocks will be in contact when the momentum of Y is increasing, right? It's initially has no momentum, it's not moving. When block X hits it, they're going to hit and it's going to have some collision time. And so the collision interval will be as the momentum of block Y goes from 0 to 0.5 here. So it's this interval here, which is 40. You have to note that it's in milliseconds, so it's 40 milliseconds. Oh, they give you it, so 40. So when the momentum is increasing, well, that's the time in which they're colliding. Okay, describe without calculation the magnitude of the acceleration of block Y from 80 to 100. Well, from 80 to 100, it's just increasing, right? So it's going to be a constant, so we've got an increase in a change in momentum, so we're going to have a constant force or constant acceleration, because force equals change in momentum over t, and force is mass times acceleration. So if we have a change in momentum here, well, with a rate of time, well, it's just going to be constant acceleration. This is going to be constant. And for 100 to 120, 100 to 120, well, the line is flat, so there's no change in momentum. If there's no change in momentum, this is 0. That means acceleration will be 0. This will be 0. Use the figure to determine the magnitude of the force exerted by the block, exerted by block X on block Y. Well, F equals the change in P over T. And from momentum, from Newton's third law, every, if one block pushes with a certain force on another block, there's going to be an equal and opposite force exerted on that block by their other block, A to B and B to A. If you just read the definitions. Okay, so wait, what am I doing? So the change in momentum is change in momentum is 0 to 0.5, so we have a 0.5 change in momentum, and the time of contact is 40 milliseconds, which is just what, 0.04? 0.0. Yeah, 0.04. 0.04. So this equals 2. 12.5. 12.5 newtons, I guess, and so rounded, two significant figures will be 13. Finally, on figure 2.2, sketch the variation of the momentum of block X Okay, so you want to see what, I guess I could change my marker here. Okay, so this is the change, how momentum is changing for block Y. Well, for block X, remember momentum is conserved. So we start off, block X has 0.4. We start off with 0.4, right? At time 0. Then it will continue to have this momentum because this is frictionless, it's not losing anything, until it hits this. So it's going to be constant. Apology for the drawing. You know, up till 60. This is 60. It then will begin to decrease its momentum because it's transferring all its momentum to block Y. But it will decrease it because it wants to keep this consistent. It'll decrease it to minus 0.10. Right? Because then minus 0.10 plus 0.5 is 0.4. So no momentum is, being lost. Momentum is being conserved. And then it will stay constant for the remainder. So actually at all points here, the total momentum of the system is 0.4. So I know it's going to go down to negative 0.1. Yeah, and so that's, block X. That's it. So that's two good examples. We will go more into the force part of it. So if that wasn't super clear, that will be the next video where we go into Newton's laws. But you've got all the questions here. We'll answer for you. You start to go through them, they ask it pretty similar every time. But the key concept here that we were introduced to was really this idea of conservation. And you have to use this idea a lot in physics and in this question. And I'm actually going to talk about the philosophy of conservation and how it can be actually negatively impacting your life and even be used against you. Okay, so here we go. I want to show you right now, or explain to you, or make clear to you that the ideas found in physics are actually governing your life, possibly without you even knowing. I mean, probably. In physics, we are saying that the universe is conserving everything. It's conserving its energy. And in the case of you, your energy will also be conserved. So you have so much energy, potential, activity, and that energy will be transformed and conserved. And society is basically a filtration for your energy. How your energy is being transformed. Society is basically trying to get your energy to fuel whatever agenda or thing that they want. And for the human being, and this is very important, so for the human being, if you want to know where your energy is being transformed or where it's going, because it's going to go somewhere, and people are aware of this, especially people in power, they're aware your energy is going to go somewhere. If you want to know where your energy is going, for the human being, their energy and these conserved properties are contained within their awareness. So where your awareness and attention is. For example, let's say that you're scrolling on TikTok for hours. You're scrolling. Well, therefore your attention is on TikTok. That means that you're transforming the energy, which is going to be conserved regardless, to TikTok. You're giving it your attention, thus giving it your energy. And you must have to reflect upon that and say, do I want to give my energy away to TikTok, let's say, as an example? Do I want to give my attention away? And I really want to hammer home or make you feel your energy and your attention is your most vital resource. And so you should be aware and conscious of where you are giving it away, because that energy is going to be conserved regardless. And so society at large is a filtration system, as I said before, for your energy. Everyone is trying, basically all the companies and businesses and stuff like this and structures are trying to get your energy. That's what they're designed for. Let's say if you go out and you work a job, you're giving away your energy on time and attention for money. You then spend that money, buy a Gucci bag or some shit. Okay, you're then that's a transformation of energy as well. You're giving away your energy in the form of money, which is now giving you this Gucci bag. And so then you've transformed that energy to the company Gucci. So you can see what I mean here. And this all comes from physics, this sort of understanding. So you have to be aware and sort of conscious of how you're distributing your own energy, because it's your most vital resource. Because how you use your energy is how you're going to use your life. I don't really know how to make it clearer than that. Your energy and attention is very important. It's your most vital resource. And I hope maybe I've given you some insight and maybe some inspiration that you should try and use it the best possible way. You know, use it like for channels like Intuitive. Give your attention away to some people that care about you, that actually give a shit and want the best for you. Maybe these companies or where you're giving your energy, they don't actually care about you. They don't give a shit about you. So do they deserve your attention? Does TikTok deserve your attention? This much attention? It's so valuable and you're just giving it away for free. I especially see that with the younger generation. But yeah, that's it. Hopefully that was insightful. Just wanted to show how physics is related directly to the functions of society and your own life. That's it. You know what to do, man. Like, subscribe. Brush up against that like button. It likes it. But I'll see you in the next one.